Okay, remember that we were doing series. So today we'll do another test. Today we'll do a comparison test. Okay, so recall that we have an infinite sum an. It's denoted to be S if the sequence of partial sums that is Sn is equal to A0 plus An. Okay, so this is the sequence of partial sum converges to S as n goes to infinite. Okay, so this is our object. And our eventual aim is to talk about Taylor series associated to functions, which is one of the main tools to understand transcendental functions. Okay, so eventually there will be a constant times x to the n here. Okay, so we immediately had noticed the following. Nth term test. Okay, so we abbreviated it like this. This says that if the general term does not go to 0, is not 0, then summation an diverges. Okay? So this is generally the first thing you check. If the general term looks very complicated, okay, then you skip this thing. But most of the time it is easy to see if the general term goes to 0 or not. If it doesn't go to 0, you stop. The series diverges. If the general term goes to 0, then you start applying other tests to find out if the series is converges. Okay, because the main question here is, given such a series, what does it converge or diverge? If it converges, what the limit is another question which we don't generally enter unless it's a very special case. And of course, we'll be interested in that when we come to Taylor series. Okay, so next we associated summation an to Riemann sums. Okay, so this gave us the following theorem, test, integral test. And again, this we abbreviated as IT. You have to put something in your arguments, such as this thing, because you say this diverges because the general term does not go to 0. And you have to say that this is because of nth term test, because if someone who is not closely following the arguments will check up what the nth term test, and he'll believe that what you said is true. So that's why we mention the key results we are using. Okay, so in the integral test, we have f is a positive continuous decreasing function and f of n happens to be an. Okay, so generally we have a formula for an. Instead of n, you put x, and then you have this function. Then you check if this is decreasing. Okay. Then summation an equals 1, or it can start anywhere, converges if and only if integral from, let's say, 1 to infinity f of x dx converges. Okay, so the main reason to invent this integral test, is to find out if P series converges or not. Because later on we'll learn many tests. None of those tests apply to the P series, and P series are very common. So this this interpretation of P series as a Riemann sum tells us precisely when P series converges. Okay? Of course, once you have such a test, then you start applying it to all sorts of funny-looking series if you can integrate the general term. Okay, so we immediately apply this. Apply this to P series. Okay, so P series is this, n equals 1 to infinity. 1 over mp converges if and only if p is strictly larger than 1. Okay, so this you can immediately find by integral test. And later on, our most frequently used test will be ratio test. And we will see that with ratio test, you cannot decide this. Okay, so we also have, then we recalled some familiar series. Okay, so one of them was geometric series. Summation n equals 0 to infinity Rn. Okay, so this starts by 1 plus r squared. Okay, so this is equal to 1 over 1 minus r if absolute value of r is strictly less than 1 and diverges otherwise. And diverges otherwise. Okay. And the other thing we were interested was telescoping series. Okay, so here we are interested in telescoping series not because it's a spatial series, but because it's a series that for small degrees we can add up precisely. Okay, so this is something of the form summation. Okay, if I write this in the general form, it looks horrible. So let me write an example here. So example 1 over n plus 1. Okay, so you write this thing as partial fractions. Use partial fractions. Okay, so n equals 1 to infinity, n equals 1 to infinity. So what is the partial fraction of this? So n, 1 over 2 minus 1 over 2. Will it be like this, or will it be just 1? Okay, so wake up. How do you do the partial fraction of this? 1 minus 1. Huh? 1 minus 1. So n's go, and we have this one. Okay. Now, when you add up these things, okay, so you use this. You use this in describing sequence of partial sums. Okay, then everything collapses and you have a general formula for the sequence of partial sums. Then you take the limit as n goes to infinity very easily. Okay, so in the quiz I'll ask you something like this, but first I will ask you to show that it converges. Now, of course, if it's not a quiz, if it's real life, you have a telescoping series, you apply this technique, you show that it is equal exactly to some number. It's a proof that it converges. Okay, but in the quiz, I want you to use another technique to show that it converges, and after that you add this up. So far, we don't have any technique to show that this converges. That will come with the comparison test. Okay, so in using comparison test, you see that this looks like this is now 1 over n squared plus n. When n is very, very large, say n has 10 million digits, then n squared is the dominant term here, and n is just a detail on the right-hand side. So this behaves like 1 over n squared. But 1 over n squared converges. Okay, so it must converge because it behaves like this. Now, what I said is just an gut feeling. Of course, people will not believe this, so we will make this argument precise. We'll call it a name. We'll give it a name, and then you'll quote that name, and then you'll say that this converges. Okay, because this behaves. You will say that this behaves like 1 over n squared because of comparison test or limit comparison test, whichever you like, and then it converges. Okay, and then the second part of the quiz is to use partial fractions. Write this as partial fractions. Use this sum in the sequence of partial sums. Then everything collapses. That's why we call it the telescoping. Everything goes to 0. You just have a few numbers plus 1 over n's at the end. 1 over n's go to 0, and those few numbers at the beginning is the sum of this infinite series. Okay, so okay, so far our repertoire of series are only these. Okay, now we want to expand this to understand further series. Okay, to develop new tests for convergence, our main technique is the following. Okay, so let Sn equals A0 plus or A1 plus An. Assume each An is positive. Okay, then Sn is an increasing sequence. Okay, an increasing sequence either goes to infinity or converges somewhere. Okay, it's either divergent or if it diverges, it goes to infinity because it's increasing. Okay. Suppose further, so this is the part that we will suppose. We manage, so not manage, but we have enough information. We have information that Sn is bounded from above. Okay, it's already bounded from below because it starts from some number, A0, and it goes up. Suppose it is bounded from above. Okay, then by monotone bounded sequence theorem, Sn converges. Okay, so that is the tool. So now in the comparison test, we'll exploit this fact. We'll have a sequence with positive, we'll have a series with positive terms. So its sequence of partial sums is an increasing sequence. Okay, now find some easily verified condition which guarantees that Sn is bounded. Okay, then you have a test. So under these conditions that we mentioned, the series converges. Okay, so the basic thing here is the following. Okay, so the basic application of this is the following. Okay, so suppose we have two series, An and Bn, and an less than or equal to bn for all large n. Okay. Okay, so you see that partial sequence for this thing will be bounded for the partial sequence of this thing. So suppose that this is one of the series that I know. Suppose this converges. Okay, then this is bounded from above by its limit. Okay, so this thing cannot pass this limit. So this is bounded. Okay, so then we have the following. If summation Bn converges, then summation An converges. And the other part, generally we use this part, but this part is also useful. If summation An diverges, okay, so now this part, this time I have information about this. I don't have information about this. I'm trying to understand this. The sequence of partial sums for this thing is going to infinity, okay, and they are always less than the sequence of partial sums for this thing, so it's also going to infinity. Then summation Bn diverges. Okay, let's give a formal proof of this thing, because the proof, first of all, is easy to understand, and also we will use this idea in developing other techniques. Okay, so proof. So let Sn be, okay, A0 plus An, and Tn be B0 plus Bn. Okay, so for the first part, we are assuming that summation Bn converges. So here we assume that limit as t goes to infinity of Tn exists, and it is equal to some number t. Okay. Then from this part, from 0, An, Bn, we conclude that okay, I add up all these things, I get Sn, but that's always positive, and this is less than or equal to Tn. Okay, so here note that Tn is increasing since Bn's are all positive. So Tn increases to T, and this is less than or equal to T. Okay? So Tn is less than or equal to T. Okay, so now we have this thing. So from here we have Sn less than or equal to T. This is an increasing sequence. Sn is increasing since An's are positive. Okay, bounded from above by T. So Sn converges. Okay, so this means summation An converges. Okay. So the trick is to pass from here to here. Here you see the right-hand side does not depend on n. That's what we are trying to do. Here Sn is also bounded, but this bound changes. If this bound is also increasing, then Sn is not bounded. When we say Sn is bounded, whatever n you choose here, this number will be less than a certain number. Okay, so that is what we are trying to achieve. So that's why we pass from this immediately to its limit. The other part is easy. Okay, here we assume that, so this is divergent, means that you are always adding something, and it's not converging to anywhere, so it's not bounded. Because if it is bounded, it must converge. Okay? We assume that as n goes to infinity, as n goes to infinity. Okay, so we have as here, okay, so here we have as n is less than or equal to Tn, taking limits of both sides. So this tells us limit Tn as n goes to infinity is infinite. So summation Bn diverges. Okay, so the idea is very simple, but this is the key idea in the next theorem, in the next test, that is limit comparison test. Limit comparison test is generally more convenient if you are trying to compare things. Okay, so this test is known as comparison test. Okay, basic application is this. So this one is, so let me write here, this is the comparison test. Sometimes we call this the direct comparison test because in a minute we will look at the limit comparison test. So this is our comparison test. Okay, so now let me come to this part. For say better test. Okay. So this is the limit comparison test. The limit comparison test. Okay. So again we have an, Bn. So some of them may be 0, but from some point on they are all positive, okay, because we'll divide by them. Okay. And assume limit as n goes to infinity of an over bn is equal to c, where c can be 0 or infinity. Okay, so let me say like this, so c can be a number or c is infinite. Okay, so we'll look at all cases. Okay, so before I immediately write this, let's understand what it means. So, so basically we are trying to understand summation an. Okay. Oh, wait a minute. Here I have comma here. Okay, so from some point on, they must be all positive, so I can divide. So basically, we try to understand summation an. Okay, and you look at summation, you look at the general term an. It's a little bit complicated, but if you simplify it in your mind, throwing away some terms which are difficult to calculate, it looks like a nice term. So, for example, in the telescoping series, in the denominator you will have lots of n minus something or n plus something product with itself. If you only look at the leading terms of these things, it will be n to the power p. So you are looking, if everything is 1 over something, then this thing behaves like 1 over np. Okay, so this is what we are trying to do. So this is your general term of the telescoping series, and this is what you would like, from your gut feeling, you say this behaves like 1 over n squared, for example. So this is your 1 over n squared. And you take the limit, and the limit is c. Okay, now let's go back to this thing. From our information we derived from sequences, this means that when n is very large, this quotient is in some neighborhood of c. It is very close to c. So it is, think of any epsilon. So this thing is, when n is very large, this thing is less than c minus epsilon. and larger than less than C plus epsilon and larger than C minus epsilon. Throw B to either side, okay? Then a constant times of Bn is less than An, and that's less than a constant times Bn. So you take either this inequality or this inequality. In one inequality, the summation Bn's are dominating summation An's. You use comparison test and say that if one of them is converging, is forcing the other to converge. Or you take the other inequality. Okay, this is the only idea. So we'll do that. But of course, you see that the reason I explained this before we come to the statement is when C is 0 or positive, when C is 0 or infinite, then it doesn't have two-sided neighborhood. Okay, infinity has only one-sided neighborhood. Okay, any number larger than something is a neighborhood of infinity. And anything to the right side of 0 is a neighborhood of 0 for us, because you see everything is positive here. We can't go to the other side. Okay, so we will have three cases. When C is positive, a real number but positive, that's one case. That's the main case here, and the book only gives that case. The other cases are given in the exercises, but we'll do them because we'll use them. It's very useful. The reason I keep talking about this is because you have to understand this. If you try to memorize this, there are three cases in which in one case summation An converges if and only if the other one converges. In one of them, there is only one side of this. In the other one, the other side. And even I don't know which one is which. So every time you have to construct this inequality, which we'll do in the proof, and immediately see what happens. Okay? Don't memorize this. Just understand that if this limit is C, whatever C is, this is in a neighborhood of C. Okay? Okay, so then the first case, C different than 0 and C different than, okay, so let me say this, 0, C less than infinity. In this case, summation An converges if and only if summation Bn converges. So this is the main part. Okay? So most of the time we are interested in, of course, our An. So most of the time we immediately write our series, the general term of our series here. And here you write the one whose behavior you know, and you are suspecting that An is behaving like Bn. Okay? So then you take this number. If this is a non-zero real number, then whatever the behavior of Bn was, you suspect it correctly. This also behaves that way. If C equals 0, okay, so since I don't memorize these things, I write this after we do the proof. And 3, if C is infinity, again, I don't memorize these things. I can't immediately write this. So I have to think for 3 seconds before I write it. So why do that? Let's go through the proof. Through the proof, it will tell us which one is this. And this is precisely what you should do when C is 0 or infinity. Okay, so the proof depends on the following thing. So first, let us look at this basic part. C is C is positive. Okay, then take any epsilon positive such that C minus epsilon is also positive. Okay. Why? We are trying to bring this to this basic comparison test. In the comparison test, everything is positive. I'll multiply, as I explained to you, Bn by C minus epsilon. Okay, so it will be this part in particular. So C minus epsilon times An, it must be again positive. So I know that this is dominated by something, or if this goes to infinity, it will push this. Okay. Then, for all large n, so in the definition of limit, it says that if you choose an epsilon, there exists an index n sub 0. So all integer for all index larger than or equal to n sub 0, we have this. An over Bn is less than C plus epsilon larger than C minus epsilon. And here we wanted to make sure that this is 0. Okay, so this is our only important part that will make this thing different. If C is 0, I'll never have this. This part is positive because ANs and BNs are positive. But, and they are also, A and Bn is obviously larger than C minus epsilon, but C is 0, then minus epsilon is negative. So I cannot use this side when C is 0. Okay, now everything is positive. Multiply by Bn, which is also positive. I will have this thing now. C minus epsilon Bn, which is positive, less than An, less than C plus epsilon Bn. Okay, so you see, this is the basic inequality. Okay, so from here we will conclude. You see, now suppose summation Bn converges. We chose this one. We suspected that this converges, so we choose something that looks like it and which converges. Okay, so this, if summation Bn converges, a constant time summation Bn converges, it dominates summation An, and these are all positive, so comparison test applies. If this was negative, of course, you can add negative things, and it will go down to minus infinity, and this guy being larger than that will not impose any condition on it. That's why we are insisting that this is bounded from below, and it is increasing. Okay, so on the other hand, if summation Bn diverges, okay, so a positive constant time summation Bn also diverges to infinity. So it will push summation Ans to infinity. Okay, so this is the basic thing. So let me write it, and then by looking at this, we'll modify our arguments when C is 0 or infinity. Then summation C plus epsilon Bn, which is, this is a constant, it comes out, summation Bn converges. And from An less than C plus epsilon Bn, by using the direct comparison test, we conclude summation An converges. Okay. Suppose summation Bn diverges. Okay. Then summation C minus epsilon Bn, which is equal to C minus epsilon summation Bn diverges. Okay. Since C minus epsilon is positive and Bn positive, this series diverges to infinity. Okay. Now I repeat the same argument here. From 0 C minus epsilon Bn less than An, by using the direct comparison test. So you see how easy it is to do mathematics. You just copy. If an idea works, you just copy it and it works. We conclude that summation An, but be careful this time, this diverges. Okay? So this is the basic equality. Coming to the other cases, we realize that if C is 0, I cannot write this, so I'll only compare this side. Okay, so let's do that. So this was the first part. The second part, if C equals 0, then no matter which epsilon we choose, which epsilon positive we choose, C minus epsilon is negative. Okay, so we cannot use the left side inequality. This is our basic inequality. We cannot use the left side of star. So what does it mean you cannot use it? If you need it, you can use it, of course. It's not forbidden, but you cannot use this indirect comparison test. Test which works only on positive terms. Okay, so that's what it means you can't use it. Because in our argument, we are reducing it to the previous test, which uses positive terms and compares them. Here we will have, if C is 0, then we have minus epsilon times Bn, which is a negative term, then it doesn't compare anything. Then we are left only with this side. Okay, so we then have okay, so 0 less than An, and that's less than C plus epsilon Bn. Okay? If summation Bn converges, then summation An converges by direct comparison test. Okay? So now I can write the theorem here. If summation Bn converges, then summation An converges. Okay, so how do you remember this now? If this limit is equal to 0, then An over Bn is less than 1. Okay, so instead of choosing an arbitrary epsilon, you see here, here we have epsilon. So instead of C plus epsilon, since C is 0, here we have epsilon. Okay, so instead of choosing an arbitrary epsilon, just choose 1. Then this ratio is less than 1. And take B to the other side, An is less than Bn for large n. Okay, then if Bn converges, it forces An to converge. Of course, we can also say here that if An diverges from that, Bn diverges, but that's just a fantasy, because normally in application you always write your own series, the general term of your own series here. This is the one you are trying to understand. You write the other test series below, so there is no need to say that theoretically. Why would I write my An downstairs? Okay, so this is the conclusion. Okay, let's look at the other one. For the other one, C is infinity, so I don't have these things. So I remember what a neighborhood of infinity is. Again, if this limit goes to infinity, instead of choosing an arbitrary epsilon or something, we understand that this ratio becomes larger and larger. Okay? Then in particular, after a while, this ratio is larger than 1. Okay? If it is larger than 1, take Bn to the other side. If Bn goes to infinity, summation Bn's go to infinity, it pushes summation An's to infinity. So that's what we will write, the third part. So the third part, if C is infinity, then for large n, An over Bn is larger than 1. So we have 0, Bn. We know that Bn's are positive. That's why I'm writing this. And now I'm writing this part like this. Okay. So hence, if summation Bn diverges, then summation An diverges by direct comparison test. Okay, so I discovered this. If summation bn diverges, then summation an diverges. Okay, so that's our limit comparison test. So how do you remember these things? This part is easy. If it is not 0 or infinity, then whatever bn does, an does the same thing. If the limit is 0, you will say yourself that then this ratio is less than 1 for large n. Then that inequality will give you that an is less than or equal to bn. I don't know what an is doing. If bn is diverging, it doesn't, or when I say when bn is diverging, I mean the series. If the summation bn's diverge, it doesn't impose any condition on an, because if summation bn's are diverging, it imposes a condition on an, because I can sometimes put it on the left-hand side. But when c is 0, I can't put it on this side. It's only on this side. So if the summation of these guys decide to go to infinity, they can, and they will not force summation of an's to go to infinity. If, however, this summation bn's converge, it will force this to converge. Okay, so that's how you recover this. If c is infinite, then it means that this ratio is eventually larger than 1. Okay, so then bn, then it means that an is larger. If summation bn's go to infinity, the series with larger terms goes to infinity. Okay, so don't memorize these parts, because that's why these parts are taken out of the calculus books. Calculus students, for some reason, always get confused here, which one was which. Okay, so don't memorize this. This part is easy, because this is the whole idea of the comparison test. If you get a non-zero real number as the limit, then whatever bn does, an does the same thing. If it is 0 or infinite, you just consider this, it is either less than 1 or larger than 1. And from there, you just conclude what's happening. So now using this, for example, okay, as an example, so suppose we have summation 1 over n plus 1 converges, okay, converges by direct comparison. Well, let's do both of these things. Let us check for convergence. Summation 1 over n plus 1. Okay, so this is an exercise, because we know that this is a telescoping series. It adds up to a real number. We know everything about this. We are now trying to test our tests if the tests work properly. Okay, so here an is 1 over n plus 1. Okay. Now you see that this is equal to 1 over n squared plus n. Okay. Now, which test do you want to apply? How do we show that this converges? First of all, let's try to apply direct comparison test. Is this strictly less than some series which we know converges? Well, how many series we know? We know only geometric series and p series. Okay, this doesn't look like a geometric series, so we will compare this with p series. This either looks like 1 over n squared or 1 over n. This is less than 1 over n. Okay, so an is less than 1 over n, right? Because I'm dividing with something else. Summation 1 over n diverges. So what? Okay, because the larger thing is diverging. Okay, he's a big brother. He can do whatever he likes. It doesn't impose any condition on this. So this didn't work. But on the other side, this is also less than 1 over n squared. Okay. But now this time, this guy converges, and it forces this to converge. Summation 1 over n squared converges. And by direct comparison test, summation an converges. Okay. Of course, you never try this. I just wrote this to show that sometimes we make an inequality like this. We know something about this, and we vaguely remember that in comparison tests, if one of them does something, the other one also does something. Okay, so memorization. So as you memorize, you say, if this diverges, then this will diverge. But you see, it doesn't make sense. If this guy must impose some condition on this while it's converging or diverging. If this was on this side, if it goes to infinity, if its sums go to infinity, then the sums of these things will go to infinity. But on this side, you can add up these things, and they can go to infinity, and this guy will just look at it and wave his hand. Okay, but here it's different. Sum of 1 over n squares converges and stops at some point. So the sum of these things, which is increasing because they are all positive, it must stop somewhere. So it must converge. We can also apply a limit comparison test to this. So let's also do that. Okay, so you look at this thing. You say, okay, it behaves like 1 over n squared. So an is equal to 1 over n squared plus n. Take, so this part is up to you. You decide which one you'll take. Bn is equal to 1 over n squared. Okay, and you look at an over bn. So this is, when you do this, this is n squared over n squared plus n. Now you take the limit as n goes to infinity. This is 1 as n goes to infinity. Okay, so this is the basic case, the main case of the limit comparison test. C is equal to 1. So whatever Bn is doing, An is doing the same thing. Summation Bn's converge. Summation 1 over n squared converges by p-test. So by limit comparison test, summation 1 over n squared plus n converges. We can also take, here we can also take, so sometimes it's not easy like this. We immediately here know that taking 1 over n will not work, but sometimes this is complicated. So you may, at first you may make a wrong decision. You learn from your mistakes, and then in the next step you'll make a correct decision. But suppose here in our first choice, somehow we thought this behaves like 1 over n. Bn equals 1 over n. Okay, then you look at an over bn. So this is equal to n over n squared plus n. So this goes to 0 as n goes to infinite. Okay, now we remember that 0 is not the main case. So when 0 is the limit, we have to think how they behave. So this means, so this is what goes in our mind. This means an over bn, since it is going to 0, is less than 1 eventually. So eventually means that for all large x starting, for all large n starting from some point. So this means, this gives an less than bn. So bn is, on the other hand, 1 over n. Summation 1 over n diverges, but this inequality does not force anything on summation an. So it is possible that summation an's diverge or summation an's converge. In both cases, we'll have this inequality. Okay, so you say that you see that this didn't work. Maybe I should take something smaller. So instead of 1 over n, now in the next thing, you try 1 over n squared, and it works. Okay, so this is how you use limit comparison test. You don't have to hit the correct check series, summation bn, correct in the first try. You try something. If it doesn't work, you try something else. Okay, let's take a break, and then we'll solve more problems, and then we'll have a quiz, something like this one.